So we'll try to give our attention. As you remember, we're partway through Chapter 6, which is about input-output in computers. So we'll pick up with the second set of slides and continue from there. All right, so we're working in this area, I/O, the fourth and fifth major component of a computer system. As you remember, in processors and even in memory, performance and cost were pretty much the only factors. It turns out in I/O, a number of factors are important, including expandability, dependability, size, cost, weight, security. Yeah, cost is in there and performance are in there, but notice it's among a list of many things. Turns out I/O is more diverse than any other part of computer systems, so we expect that we're going to be more challenged to design it. And I guess you've noticed as a computer user and as a future computer engineer, there's much more diversity in I/O systems than there is in memory and processor. Processor and memory systems have got some pretty much classic standardized answers to the questions. Whereas I/O, a lot of the questions are still open questions. There's a lot of research still going on. So are there any questions that you'd like to ask as we begin? This is the introduction to our final section of the computer architecture. We worked our way through processor with control and data path, spent time in memory and the memory hierarchy, including disk, and now we're in the final section of input-output devices. Anything that you'd like to ask or mention before we begin? Okay, then here we go. All right, a typical I/O system is based around a bus connecting a variety of I/O devices to the processor and memory. So you can see that the processor's got a close cache and memory which it can access, but we're going to have other devices as well, disks, graphics, networks, et cetera, et cetera, et cetera. They're very different from each other, but they share one thing in common. They all have controllers. Disks have controllers, graphics have controllers, networks have controllers. Every I/O device has a controller. And the controller is simply a piece of hardware which interfaces the I/O device to the different levels of the rest of the system, including the physical bus interface and signals and timing and protocol, but also the addressing of its memory items, giving, reading or writing from the, this is where there'll be buffers and data coming in from I/O will end up eventually in memory and going to the processor. Data going out to I/O will go first to those buffers and then out. For example, graphics controllers are output devices, disks are input-output, networks are input-output. Okay, so this idea of a single shared memory bus is a little bit of a oversimplification. In fact, we'll have a memory bus and an I/O bus usually which are different speeds and different performance levels. One more thing. Do you notice that when necessary, I/O devices have the ability to interrupt the processor and say, hey, I need some service. I've got data for you to take, or I finished writing out the last data you gave me, or I've had a problem here, I'm out of paper, or we've had a hard drive crash, or the network isn't responding, whatever. But these interrupts tell the processor about the status, positive status as well as problem status. So we have, in this model at least, interrupt-driven I/O. The interrupts tell the processor, I did what you asked, or I'm ready for the next one, something like that. Any questions? Okay. All right, as we said, I/O is pretty diverse. There's quite a wide range of I/O devices, and you can see that some of their speeds are listed here, and their data rate varies from keyboard, which is about as fast as the human can move a finger, extremely slow data rate, to extremely high data rates for high-speed LANs and graphics displays. Those are in enormous numbers of megabits per second. The partner for an I/O device may either be a human or a machine. On the other end of the line, for a network, the other end is a machine. On the other end of a graphics display is a person looking at it. Data rates vary. The behavior may be I/O, input, output, or storage. So there's quite a diversity. 8 orders of magnitude range between slowest and fastest. Nothing like that in the processor or memory world. Okay. Now, how to measure performance? We said performance is part of what you might want in I/O, but are you looking for bandwidth, how to shuffle the data as fast as possible, or looking for latency? How long till I get the first response? Bandwidth and latency, as you remember, are very different. We looked at those in terms of processor performance, and throughput is essentially bandwidth, and latency is essentially response time, and they're very different from each other. So some situations want bandwidth or throughput, some situations want response time or latency, and the situations are different from each other. The amount of information that you can input or output and communicate across an interconnect in a fixed period of time. So it'll be in megabits per second or gigabytes per second or something like that. How much data can you move through the system? That's it, the rate of data that's going into the outputs or coming in from the input devices. Or maybe something like this, how many I/O operations can you do per second? An ATM machine is connected to the main processor in a banking system, and so a transaction is one thing that the ATM machine is saying, please do this, update the balance, and please send it back to me so that I can display it. Or please, tell me if there's enough money in order to give the amount that's been requested. Those are called transactions. They involve I/O operations. Okay, response time is the total time it takes to do a single an input or output operation, or the total time. It'll mostly involve the time to get it started. If bandwidths are high, then the major amount of time will be to get it started. Especially it's important in real-time systems. We want to know how long does it take to get that thing done. And many applications require both high bandwidth and low latency, and of course you can imagine that those are going to be expensive if you ask for both at the same time. Did I miss one there? No, that's right. Okay. Now, I/O obviously is a diversity of devices. It has to be connected. So we've got to connect these various input and output devices to our memory and processor. So the basic connection metaphor is a bus. Even if it's a serial bus with very few wires. The old name bus involved large numbers of parallel signals. But even if it's a serial bus, like USB, Universal Serial Bus, we still call it a bus. It means it's an interconnect system. Bus's old meaning has changed to just mean connection system. Okay, and it's a single set of wires that connect multiple subsystems, at least two, maybe more, that need to support a range of devices that have different latencies and different transfer rates. Now, if you use a bus, you get some advantages, but you also get some disadvantages. Okay? Well, let's have a look at it. Buses are versatile and they're low cost. Basically, the bus is just a passive system with active transmitters and receivers on the ends. It doesn't cost much to make a bus. It's a cable or a set of wires on a motherboard or something like that. So they're low cost because you're able to share the wires. In other words, if we have a bus, you and you and you and you and I can be connected to it. If we don't have a bus, I have to have a connection to you, I have to have a connection to you, I have to have a connection to you, you have to have a connection to her, you have to have a connection to him, you have to have a connection to me. Pretty soon you can see it's going to be n squared connections. But with a bus, it's one connection and it's shared. So it's low cost. And it's versatile. It means that we could add new devices easily. Once we have a bus, then we can put you on the bus as well. We have a bus, 4 users. You can become number 5, as long as you know how to obey the bus's protocol, voltage levels, timing signals, etc. So if you have the right bus interface, you can join the bus. So therefore, you have bus standards and devices that are made to adhere to that standard or plug and play. You put them on and they're on the bus, and now you added a new I/O device. Now the disadvantage, of course, is just as you can kind of feel, wait a minute, after 4.5, after 5.10, after 10.50, after 50.100, isn't it going to get a little crowded on the bus? I don't know if any of you go ride Ankara's city buses, but at certain hours of the day, you can be very crowded. Not only is there no room to sit down, there's no room to stand. They're just packed, like a can of, Humpsy or something. And you feel yourself to be one of those sardines in the can. You're thinking, when can I get off? Or at least I hope they get off. It's very, very crowded, isn't it? Okay, and in the same way, if you overload a bus, what's going to happen? You're going to have bandwidth limits, which are going to cause throughput problems. It's going to be a bottleneck. It's going to be a darboise, right? So buses, if you overload them, have that disadvantage. Their performance is limited to the bus's transfer speed. The more devices you put on a bus, the less of the bus's capacity can be given to each device. You say, I need to use it, this much and this much and this much. Well, if it adds up to more than 100%, it can't be done. So the maximum bus speed is usually largely limited by the length of the bus. The longer it is, the lower its transfer speeds, and that's because of literally wavefront propagation time of electromagnetic signals going down the bus. That'll be one of its limits. Longer buses are slower. And the second thing is the number of devices on the bus. The maximum bus speed is limited by the number of devices, as well as its length. Okay, so you know some bus standards. We'll talk about some right now. There are many, many more. Buses are a wide variety. There's no single one architecture for a bus. There's no single one solution that fits all. Did I ever tell you my story about one size fits all? Okay, whenever I hear about standard solution. It happened on the streets of Istanbul years ago. Did I ever tell you this story? Okay, then let's take a little break and tell the story. I think you'll find it entertaining. There was a lot of street vendors, as there are. I mean, the Zabita are not able to chase away everybody. So, and these guys are fast. They're able to wrap up and run, you know. So when there's no Zabita around, they're out there selling their stuff on the sidewalk. No rent, no electric, no water. You know, it's nice. No tax. It's all profit. And so I was walking along on a kind of a dreary November day. If you know Istanbul weather, you know that it tends to drizzle a lot. And before natural gas came, there tended to be a lot of coal dust and ash that just kind of went out the chimneys and then slowly settled on everything. So all the housewives and cleaning people were busy, always cleaning up. Now it's a lot better because of the oil gas. Anyway, I'm walking along, and there's this sweater seller, right? And it's November, it's getting a little cold, so I thought I need a sweater for winter. My wife said, "Oh, that's beautiful." It was a nice yellow sweater. I liked it too, you know, a nice bright color, catches your eye. So I said, I leaned over and looked at it, and the guy thinking, great, he's looking, he stopped, all right, you know. And so I said, how much is it? And we talked the price. And then and I said, can I see it? Well, the first thing he did was take a little broom and whisk off all the coal dust ashes, which had landed on the nice, pretty yellow sweater. And then he held it up. And I said, you know, I'm not sure it's going to fit. Oh, yeah, don't worry, it's going to fit. And I said, but I'm got long arms, and I'm really skinny in the middle. I'm not sure. Is it my size? He said, size? One size. There's a standard size. One size fits everybody. And I said, don't you have like 38, 40, 42? No. Don't you have even small, medium, large? No, this is just it. This is the standard size. One size fits all. I'm translating it. It would be even better in Turkish. But anyway, and I said, one size fits all, but I'm not standard size. Look at me. And then what he did, he started pulling on the sleeves to make them longer and kind of pushing the middle in. And he pushed it up to me. He says, there, see, it looks good. And my wife looked at it. She's like, no. So I gave it back to him. He was so disappointed. He couldn't understand, why aren't you, you know, the standard size? The sweater wasn't made for me, but he wanted to make it for me. Anyway, the buses are non-standard. I mean, there's lots of different kinds of buses. Let's have a look at some of the few here. Processor memory buses tend to be very unique. Proprietary means property of that company. Okay, so they're specially designed between processor and memory. So called front-side buses. These are short, they're high speed, they match the memory system that's been designed for the processor in order to get maximum bandwidth. And they're optimized for cache block transfers. So a lot of design parameters make these special and non-standard. Okay, then the I/O buses, which are industry standard. You've heard of a few of these: SCSI, USB, FireWire, etc. These are standard industry buses. Usually they're longer, they run slower. You wouldn't use them for processor memory, you'd use them for I/O. They accommodate a wide range of I/O devices. All kinds of things can be USB and SCSI and FireWire. They use either the processor memory bus or the backplane bus to connect to memory. So they don't directly connect to memory, but they connect onto another bus which gets to memory. So therefore there's a path from I/O devices to memory. And then there are things called backplane buses. It was mentioned here. A backplane bus is also industry standard, and you get these sometimes on the motherboards like PCI Express or ATA. And these allow a processor and memory and I/O to all coexist on a single bus. Processor is on the backplane bus, memory is on the backplane bus, I/O is on the backplane bus. So one bus. But the problem, of course, of one size fits all is the story of the sweater. Okay, you know, in order to do that, you're making some compromises. Sometimes these are used as an intermediary bus connecting the I/O buses to the processor. That means that, well, now we're going to boost it up and make it high speed, the backplane bus, and we'll have lower speed I/O buses. If you take out the I/O, now the backplane bus essentially starts to function as a standardized processor memory bus, saving you this design time. But if you leave I/O in, now it's one size fits all, and it has to go as slow as the slowest device. Okay, any questions so far about this concept? These are general ideas, but you can see that we've got devices, controllers, and buses. Those are the three topics that we've talked about. We've also tried to emphasize big diversity, one size doesn't fit all, no given fixed solutions, lots of interesting room for possibilities of engineering here. Now, an I/O transaction is a sequence of operations that include requesting and getting access to the I/O bus and then to the device that you want to communicate with. Maybe it's a control transaction, maybe it's a data transaction. The transaction is initiated by a single request, but it might take many individual bus operations. So an I/O transaction is talking about individual operations on a bus in order to get a job done, whatever that job is. Disk block read. Okay, a disk block read is a single I/O transaction, but it may involve a bus protocol and some communication over the bus that takes many individual bus operations. You got to send the address, and you've got to either send the data if it's an output or receive the data if it's an input. So you can see that we're going to use the bus at least 2 times for address sending and then for data sending. And there may be some getting the bus if there's competition over it. There may be a potential for a conflict, so you have to eliminate the conflict, get the bus, do this, and then finish the handshake. So there's usually what's called a handshake. We'll show that on a little bit later slide. Bus transactions are defined or referred to or named according to what they're doing to memory. A read transaction is reading data out of memory. Okay, that means it's going to go out somewhere. And a write transaction puts data in the memory. That means it's bringing it in from somewhere. So inputs from I devices do write transactions to memory. And outputs to O devices read from memory. So they're considered bus reads. Okay? So bus reads and bus writes are defined according to memory, not what's on the other end of the bus, namely the input or the output device. So inputs are the write transaction and outputs are the read transactions. Now there's 2 kinds of buses, synchronous and asynchronous buses. Synchronous buses, you should immediately ding, 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 say, oh, those must have a master clock. And everybody's agreed to a certain set of fixed timing signals. Asynchronous means, esté agarré, and no timing master, just whatever kind of a handshaking protocol can agree. I've got something, you say, great, send it to me, I say, here it is, you say, thanks, I got it, and we're done. There's no master timing. If you're slow, then I slow down for you. If I'm slow, then you slow down for me. We go at the rate of the slowest. So if I have a slow handshake, I say, here's some data. You say, great, I'll take it. And then I say, here's the data. You say, thanks very much, I got the data. There's no master synchronizing clock. If there's a master synchronizing clock, then we both have to be able to obey that clock's tempo and timing. The nice thing about asynchronous is it allows devices of different speeds to work on the bus, whereas with synchronous bus, everybody has to say, yes, sir, como tan, according to the timing of the master clock. So there's a difference in flexibility there. The disadvantage of a clock here, okay, it's light on logic and you can get high speeds, but every device has to use that same clock rate. So that means the synchronous buses have to be as slow as the slowest device, or another way to say it is some devices may be too slow and they can't be on a synchronous bus. So that's good, but it's bad. And then you also have clock skew, just like we had it in sequential design. If the bus gets too long, you get clock skew problems and it won't time right. Okay, so it limits the length of the bus as well. Asynchronous buses say clock, schmock, mock, knock, we don't do clocks. Great, so you're free from all the disadvantages. Now you have handshaking protocols. I'm fast, you're slow, hi. Okay, I'm ready to take your data. Okay, here it is. Okay, we can do that. See, so now you can have devices with different timings be able to communicate data to each other. It's not clocked. You have a handshaking protocol which would involve, I'm ready to read, okay, the data's ready, okay. So we'd have acknowledgments for, think about it. In a human handshake, that says I'm ready, and the other one is the acknowledgement. Okay, I'll be your friend, I'll introduce to you, let's shake hands. Then, okay, now they're held. You've been in this, haven't you? Hey, it's nice to meet you. Somebody's going to let go first. And sometimes there's this decision, hey, I'm not going to be the one. And so it just stays there, and they're talking. But somebody lets go, and then the other one doesn't just keep their hand out. They say, okay. So there's a 1, 2, then there's the transfer. That's the data in this analogy. Then there's the 3, and then 4. So just like that. The advantages of using an asynchronous bus are it can accommodate a wide range of devices and speeds. And it can be lengthened without worrying about timing problems and bad data transfers. You can make the bus as long as you want. There's no synchronization problems because it's asynchronous. The only disadvantage is they tend to run a little bit slower. Okay, now, ATA. Serial and parallel. You know the difference. Parallel says I have a lot of wires. All the bits go at once. Serial says I have a few wires and the bits go ARDA ARDA, right? The green cable is parallel ATA. The red cable is serial ATA. You can see that the cost and size and flexibility are hugely different here. And you might think, oh, well, then more bits in parallel will be better. I'll get higher data rate in parallel ATA. In fact, you're completely wrong. Turns out when you get a lot of lines in parallel, their crosstalk, the electromagnetic signaling that they affect with each other, makes the clock rate have to go low. Slow it down because of all this parallel hardware. As soon as you allow a serial bus with just two and you are allowed to twist them, then the electromagnetic crosstalk cancels and you can go at really blazing high speed rates. So serial buses tend to be way faster in clock rate than parallel buses, okay? And also much thinner and cheaper. So how can you lose? Smaller, lighter, thinner, more flexible, less costly, and faster data rate. Win-win. Thank you very much. Okay? Look at the combinations here. You can run these serial buses at extremely high, 2 gigahertz clock rates, and the parallel ones are sort of limited because of their massive number of wires. So as a consequence, you know, when you try to do 64 wires in parallel, you just can't get higher than, you know, megahertz range. Okay, now let's talk about handshakes. We mentioned the handshake idea. Okay, this slide is going to show which signals initiate and then follow. I think basically you might say that we're going to do an output from memory to an I/O device. So that means that we want to read from memory, right? So there's going to be a read request and an address and then later the data. So where do you want to read from? Okay, great, here comes the data. You can see that blue is the I/O device and black is the memory in this. So the I/O device says, hey, I want to read you. Here's the address I want to read from. The memory says, okay, great, we'll do it. Here's the data. But that's not all that memory says. Memory says, I acknowledge you requested to read. Hey, I saw it. Here's the read request. Okay, I'll let you read that address. Or I'm letting you. I've got it. I got the address. Okay? And then a little bit later, when the data comes out, the memory says, here's the data, Buiren, with data ready. And now it's the I/O device's turn to say, I acknowledge. Got it? So the first one is I/O says, I want to read you. Memory says, okay, we can do that at the address you gave me. The second one is memory says, here's the data I'm offering. See those? Here's the data I'm offering. And the I/O device says, great, thanks, I got it. Acknowledgement means I got it. So notice this happens in parallel with this, and the other device later says acknowledge. This happens in parallel with this, and the other device later says acknowledge. That's what a handshake is. It's an electronic sequence of signals, of timing signals, which are very analogous to humans shaking hands with each other. This doesn't really work. You know what I'm doing. All right, so here we go. Those two happen, and then they get acknowledged. And then as a consequence of the acknowledgement, the I/O device says, great, then he's got the address. I don't need to keep it anymore. I can drop this and let go of that. So those are taken away. So that's the first part. And then, sometime later, because of this, from the I/O device, the memory says, oh, okay, I don't need to hold the acknowledgement high anymore, so I can drop that. So the whole first phase is this. Everybody's low again. Now it's time for phase 2. When the memory actually has the data, it was given an address, now it goes and gets the data, because there's some delay time between getting the address and reading the data out. Then memory says, okay, here we go. I'm now going to put the data out and give a data ready signal. And then a little bit later, the I/O device says, great, I got the data and I'm acknowledging it. And then a little while later after that, the memory says, great, I saw your acknowledge, so I'm going to let go of my data now and let go of my data ready signal. And a little while later after that, the I/O device says, good, well, now that you've got it, I'll let go of my acknowledgement signal. Any questions about this? So it's 2 handshakes. Phase 1 is the address, I/O to memory. Phase 2 is exactly like it, but it's the other way around. It's the data, it's memory initiating and I/O responding. This is what we call handshake protocols. There is no master clock. There's no master clock. So you might say, well, what happens if one's fast and one's slow? Then we'll just stretch out some of these timings because of the slow one. It won't be able to respond as quickly. If you have fast devices, these distances will all shorten because they're both able to do it quickly. That'll be an internal timing issue related to the I/O device and its controller. Okay, got any questions about this? I hope this is clear, but if it's not, I'm happy to wait here and have a little discussion. This is important. This is how buses work, at least asynchronous buses. And handshaking, this asynchronous thing actually has got software analogies. Two communicating entities, two processes are trying to exchange data in a coordinated way with each other. They'll have to do something like this too. They'll have to do something like this too. Unless there's just a place to put it. If there's a shared memory, one writes it and goes away. It says, hey, brachte miste die in zaman gelal. Right? But here there's no place to leave it. It's on the bus, and it has to stay on the bus until the other side says, okay, I got it, okay, I got it. In that case, then it's taken. Yeah, you have a question?
Yeah. For the redirect sign, why does it drop at the end of the address part? Why doesn't it come to
Read request, this one here? Okay, well, this is when it says, I'm requesting that you read this data. And when it knows the address has been read, then it says, great, now I can drop. See, this says, I got it. This delay says, when you say acknowledge, that means I took that address, thank you very much. And I'm telling you that by raising acknowledgement. Well, now you know you don't have to keep the address on the bus anymore, and you know you don't have to say read request anymore. I've read it. So therefore, you drop that, and that tells me I know you got it, so I can let go of this. 1, 2, 3, 4. Watch again. 1, 2, 3, 4. Exactly that. Yeah.
Would it be a problem how many once cancel the data?
Cancel. You start it and then you don't want to continue with it. Why would you do that? Why would you say I want to read and then you changed your mind after you said that?
Maybe the reading process is long and I want to cancel, but I already zeroed the reads.
Yeah, once you start this chain in motion, you have to finish it. So the only thing you can do then is just throw away the data. Once you get it, once you start a read, you need to finish it, then you can throw it away. Unless we have another control signal. If we have one more here called abort, cancel or something, then we could use that. If that ever goes high, then both sides forget. What's happening is both sides are moving through a set of states. Imagine a state machine with 4 states. So we start here and we're waiting for the other side to do something. That moves me to here and I send something back. When I see that he sent something back, I go to here. And then when I send something to him and when I see that he sent it back, I go back home. So they're both running around a set of states. There's 2 independent state machines, and the output of one is the input to the other, and the output of one is the input to the other. So we've got 2 coordinating state machines. And as you know, state machines can be designed to run synchronously on clock changes, or they can be designed to run asynchronously on input level changes. So you can make these state machines clocked internally in device A and device B, or unclocked if you want to have them unclocked. Okay? Doesn't matter. Anyway, but the idea is there's 2 state machines. So once we start into the sequence of changes, unless there's something that says go back home ET, we're going to finish it and get back to the starting state again. Now, if you don't want the data, then you cancel it from a higher level. You say, yeah, Bosch fair, throw it in the trash. We don't want it. Sorry, I started it, excuse me. Jan Schapt. But you have to go through the protocol. So this is called a protocol. This is a bus protocol, a real simple bus protocol. Okay, let's push on a little bit. Some I/O standards, just a few are listed here. FireWire, USB 2.0, PCI Express, Serial ATA, and Serial SCSI. Okay? And you can see that their use is external to computers versus internal to computers. These will be on motherboards inside. This will be going from the box out to some external I/O device. How many can you hook up together? Most of us may know. No, you can put 127 devices on a USB bus. Most of us just stick one. Right? But FireWire 63, and then these all 1, and SCSI will take up to 4. Maximum length. Look, the inside the box ones are smaller, except for that one. The outside the box ones are longer. Remember, we talked about bus length, and it's related to the bus speed and number of devices. Data width, 4 bytes, 2 bytes, 2 per lane, 4 on 4. Peak bandwidth. How fast can this bus transfer stuff? 300 megabytes a second, 300 megabytes a second, 250 megabytes per second per lane. Well, look, it comes as many as 32 lanes. Oh my goodness, 32 lanes times that's going to be in the tens of gigabytes, right? 0.2 megabytes per second. I think all of us are aware, aren't we? USB is a slow bus. It's an external, slow, cheap bus. That's why it's so popular. Doesn't transfer data very fast. Okay, you can go a little bit faster for full speed and high speed, but nothing along the lines of those numbers. And then here we have a 50 megabyte per second or 100 megabyte per second bus, depending upon which FireWire version you get. Hot pluggable means when everything's turned on, can I stick it in? Yes, 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 and it depends. Maybe you should turn the system down, put in another PCI card, and then turn it back on. Depends on some other factors. So those are some characteristics of standards. What do you see there? Diversity. Diversity. Every line has got some pretty big range. Just look on every line. There's large diversity between the minimum and the maximum number on every line, even yes and no. So there's a lot of difference among I/O standards. And these are standards. These aren't proprietary where your company designed it specially. These are the ones that are available and widely sold. Okay, here's an architecture that I think all of us should be very aware of. Typical I/O system. We've got here one or maybe two processors or cores that connect to what's called a north bridge. This chip is a memory controller. Its main job is to interface processor to memory. Okay, here's main memory. The caches are going to be on chip here. This memory controller is going to have built into it all the things related to memory management that we talked about. And it can handle, as you can see, extremely high data rates, 5.3 gigabits per second. On the other hand, these front side buses can do 10.5 gigabits per second. So if you have two of these, you have an enormous data transfer capability here. The North Bridge memory controller's other function is just to interface to the rest of the I/O world. Does everybody see this is the I/O world here? This is processor and memory here. If we never did any I/O, this would be totally sufficient for high performance computing. But we do I/O. That's the whole reason that you and I can give things to a computer and get things from it. And these are not exactly slow, but relative to 10 and 5.3, these are slow, so they're slow, 2 gigabytes per second for PCI Express or ESI. Now, the South Bridge chip is an I/O controller. So just as this is a memory controller because its main job is this one's job is to interface to the wide variety of I/O devices and I/O buses. Will you look, please? I've got serial ATA. I could have parallel ATA. I've got low-speed things for keyboards and mouses. I've got USB. I've got PCI Expresses. I've got PCI X's. I've got parallel ATA. All diversity, but this chip has been built to allow a certain number of this kind, this kind, this kind, this kind, that kind. So these buses, Thursday buses, really just have two members. One is the I/O device on one end, and the other is the chip on the other end, keeping the distances short, keeping the numbers of devices small. It's better to have two serial ATAs with different disks than one with two disks on it, right? So you can add these ports with transistors here cheaper and get better performance than putting two disks on the same bus. Anyway, that's an idea. Now, it turns out these memory controllers, because of such large amount of available transistors on the chips, are becoming integrated into the chips. So instead of a chipset, so there's a chipset with 1, 2, now we can go down to 1 because this is starting to migrate into the processor, so leaving us only a single I/O controller chip. Understand? Okay, so what we've got is you need a processor chip. In the old architecture, you need a north bridge and a south bridge, and you've just finished your system configuration. You need a motherboard to connect everything together. In newer architectures, you need a processor chip, and you need your I/O controller chip, and they're done, plus your motherboard to connect everything. This is pretty basic system architecture. Now, your motherboard manufacturers will lay this out differently and choose different chipsets, and you know that the chipsets that can come with motherboards vary, et cetera, et cetera. And memory can vary as well, and processors can vary as well. But basically, you're looking at processor, memory, and I/O with connections and bus controllers. Okay? Connections and bus controllers. And we've minimized the connections here. A lot of transistors inside here to allow, you can imagine this is a giant switch. And this is a very fast switch as well. So this is switching between input coming in, output going out, memory traffic to processor and to I/O devices. Okay? Well, this is controller. Smart algorithms are running inside this as well as inside this, and high performance stuff. Okay. I think that's a good place to take a break. So why don't we have a 10-minute break? And when I say 10, I mean 10. Don't take 15. Come back in 10 minutes. We'll continue the class. All right? Everybody catch some oxygen and a cup of coffee.